When you think of math, what's the first thing that pops into your head? For a lot of us, it's probably smooth curves, calculus, finding the area under a line that just flows perfectly. But what if I told you there's a whole other side to math? A world that's built not on smooth ramps, but on individual, separate, distinct steps. Well, welcome to the world of discrete mathematics.
And this slide right here, it perfectly captures the two worlds. On one side, you've got continuous math, that smooth ramp. It's all about real numbers, things that you can chop up into smaller and smaller pieces forever. But on the other side, you've got discrete math, and that's our flight of stairs. Each step is its own thing. You're either on step 3 or step 4. There is no step 3.14. It's all about things you can actually count. So now that we've kind of seen the difference, let's get a little more formal about what this other side of math really is. It really just boils down to a simple idea: the difference between counting things and measuring them.
So at its heart, we're talking about things we can count, one by one. Think about people in a room or the steps on that staircase. These are things made of separate parts, and there's just no in-between.
And this quote from Norman Biggs just nails it. If you can count it, it's discrete math. And yeah, that counting could go on forever, like when you're counting integers, 1, 2, 3, and so on. But the key is that each item is distinct and separate from the next. Now, this might sound a little abstract, but this focus on countable things is exactly why discrete math basically exploded in importance with the invention of computers. I mean, think about it. A computer runs on discrete steps. It stores data in discrete bits, ones and zeros. You can't have half a bit, right?
So how does this all work in the real world? Well, I like to think of discrete math as this incredibly powerful toolbox, specially designed for our digital age. So let's open it up and take a look at a few of the most important tools inside.
First up, we've got logic. And this isn't about winning arguments with your friends. In math, logic is all about the fundamental rules of the game for reasoning and for making valid arguments. This is, and I mean this literally, the bedrock for how computers think. Every single decision a program makes, every calculation a chip does, it all comes down to processing a massive, massive number of discrete, true, or false statements. Logic is the rulebook for that whole process. Okay, next tool in our box is combinatorics. Now, if logic is the rulebook, you can think of combinatorics as the art of arranging all the pieces on the game board. This is all about the amazing power of counting arrangements. I mean, how many different passwords can you possibly create? How many different routes can a little packet of data take to get across a network? Combinatorics is what gives us the tools to answer those kinds of questions, and with absolute precision. And finally, we get to one of the most visual tools in the entire toolbox: graph theory. And no, we are not talking about the pie charts and bar graphs you made in school. This is something else entirely.
See, in this world, a graph is just a network of dots, we call them vertices, that are connected by lines, which we call edges. And these super simple structures, they are unbelievably powerful. They can represent pretty much everything, from your network of friends on social media to the actual physical layout of the entire internet. Okay, so we've got these tools: logic, combinatorics, graph theory. They sound cool, but what do they actually do? Well, this is where it gets really exciting. This is how this other side of math is shaping our daily lives in ways you probably don't even realize.
This timeline really shows how these ideas grew. It started with what seemed like simple puzzles, like how many colors do you need to color any map so no two bordering countries are the same? But then, real-world pressure, like the desperate need to break codes in World War II, totally supercharged its development, and that led directly to the birth of the first modern computers. And this table here makes that connection just crystal clear. Every single time you shop online and see that little lock icon, that's number theory, a branch of discrete math, protecting your credit card info. When your GPS finds the fastest route, yep, that's graph theory at work. The logic gates humming away in your phone, the way data is organized to keep networks secure, it is all powered by the tools from this toolbox. But here's the thing, the story is not over, not even close. Discrete math isn't some old, dusty, settled field of study. It is a living, breathing area of research with huge, absolutely mind-bending mysteries that we have not solved yet. In fact, there is one question that just towers above all the others. It's a challenge so deep, so profound, that solving it could change,
Well, pretty much everything we know about computation, and maybe even problem solving itself. It's known as the P versus NP problem. So to put it simply, P problems are problems that are easy for a computer to solve. NP problems are ones where it's easy to check if a proposed answer is correct. So the big question is, if an answer is easy to check, does that mean the problem is also easy to solve? This gets right to the very heart of what is easy and what is fundamentally hard for a computer to do.
This problem is so important that the Clay Mathematics Institute has put up a $1 million prize for the first person to come up with a correct proof. It is one of only 7 Millennium Prize problems in all of mathematics. That's how big a deal this is.
So what's really at stake here? This question, which is rooted deep in discrete mathematics, it isn't just for academics. If it turns out that P equals NP, it could unlock solutions to some of our biggest challenges, from curing diseases to predicting climate change. But if P does not equal NP, it could prove that some problems are, and always will be, forever beyond our practical reach. The answer, whatever it is, will help define the very limits of what we can achieve. So what do you think it is?